Estimation of percentage of iron in hematite ore by external indicator method. You know that except noble metals, that is gold, platinum or palladium, all metals exist in the form of oxides or sulfides, sulfates, carbonates or silicates. These combined forms are known as ores or minerals. Natural occurring metallic compound is known as minerals. The mineral from which metal can be extracted economically is known as ore. Iron exists in three forms. In oxide form, Fe2O3 is known as red hematite. Hydrated Fe2O3 is known as brown hematite. Fe3O4 is known as magnetite. In sulfide form, it is FeS2, that is pyrites. In carbonate form, FeCO3, that is siderite. Commercially, the iron is obtained from hematite ore. The best hematite ore contains 69.4% of iron. Hematite ore mainly contains iron oxide and small amount of silicon. To estimate amount of iron in hematite ore, first we have to prepare ore solution. The ore solution can be prepared by treating known amount of hematite ore with 1:1 HCl solution, and the solution is digested on a water bath. During digestion process, the iron oxide is converted into ferric chloride and silicon oxide is converted into hydrated silicon oxide. Is an insoluble residue and can be removed by filtration. The filtrate contains ferric chloride solution. This process takes minimum 2 to 3 hours, but you know that we have to perform 2 experiments in a span of 3 hours. That's why we will provide the prepared ore solution. To estimate amount of iron present in the given ore solution, you have to prepare standard potassium dichromate solution. But this ferric chloride solution cannot be titrated against potassium dichromate solution because both are oxidizing agent. We have to reduce ferric chloride to ferrous chloride, then you have to oxidize. The amount of dichromate required to oxidize ferrous to ferric is used to calculate the amount of iron present in the given ore solution. Stannous chloride is used to reduce ferric chloride to ferrous chloride. The reaction between the ferric chloride and stannous chloride is rapid and quantitative in hard condition. That's why we have to heat the ore solution nearly to boil, then you have to add stannous chloride dropwise. The completion of this reaction can be identified by absorbing the change in color. The ferric chloride, that is ore solution, in hard condition in presence of HCl is golden yellow color. That golden yellow color changes to colorless. The colorless solutions indicate that we have reduced all ferric ions to ferrous ions. After getting colorless, we have to add 1 or 2 drops excess to ensure complete reduction. Excess stannous chloride can be destroyed by adding mercury chloride, but we have to add mercury chloride in cold condition. The reaction between stannous chloride and mercury chloride can be identified by absorbing the change in color. The colorless solution changes into the silky white precipitate. The silky white precipitate indicates that we have oxidized excess stannous chloride into stannic chloride, and that silky white precipitate is due to the formation of mercurous chloride. Now we can titrate the reduced ferric chloride solution, that is ferrous ions, against the potassium dichromate solution. The dichromate oxidizes Fe2 plus to Fe3 plus, and ferrous ions reduces chromium 6 plus to chromium 3 plus. The completion of this reaction can be identified by using the potassium ferricyanide as an external indicator. First part is preparation of standard potassium dichromate solution. Weigh around 1 to 1.2 grams of potassium dichromate salt and transfer into the standard flask. Again, take the weight of empty bottle. The difference gives the weight of salt taken. Add water. Wash the funnel. and sides of the flask. And dissolve the salt. Add water up to the mark. Mix well for uniform concentration. And fill this burette with this standard solution. Second part is estimation of iron in hematite ore. We put out 25 ml of prepared ore solution. Into a conical flask. Add 1:1 HCl solution of this tester. Now we have to heat the solution nearly to boil. If one or two bubbles appears, stop heating, add stannous chloride dropwise till it changes to colorless. How to add stannous chloride in hard condition, dropwise till it changes to colorless. The colorless solution indicates that we have reduced all ferric ions to ferrous ions. After getting this colorless solution, add 1 or 2 drops excess to ensure complete reduction. Now cool the solution to room temperature. Open the tap and cool the solution. Now add 5 ml of mercury chloride. You have to add mercury chloride in cold condition. Suppose if I add mercury chloride in hot condition and in the presence of excess stannous chloride, mercury chloride reduces to metallic state and gives black precipitate instead of white precipitate. If you get black or grey precipitate, you have to discard the solution and repeat the experiment. That's why you should not add excess stannous chloride, and we have to add mercury chloride in cold condition rapidly. This white precipitate indicates that we have oxidized excess stannous chloride into stannic chloride, and this white precipitate is due to the formation of mercurous chloride. Add 1 tablespoon of distilled water to avoid loss of ferrous ions. Place a number of drops of freshly prepared potassium ferricyanide indicator on a wax paper. Take around 200 to 250 ml of water and keep the glass rod in beaker. First add around 5 ml of the potassium dichromate solution. So in addition to potassium dichromate solution, we can see the change in color of the reaction mixture. It changes to greenish color. This greenish color is due to the reduction of chromium 6 plus to chromium 3 plus by ferrous ions. Now remove the drop of the reaction mixture and bring it in contact with indicator drop. Here the reaction mixture contains ferrous ions, indicator contains ferric ions. The ferric ions oxidizes ferrous ions to ferric ions, and these ferrous ions reduces ferric ions to ferrous ions, thus forming a complex called as ferroferricyanide, that is called as Turnbull's blue, or ferriferrocyanide complex, that is called as Persian blue. So this is intense blue color is formed due to those complex. After dipping into the reaction mixture, this glass rod should be washed with water. That's why I have taken water in the beaker. You should not dip into the reaction mixture. First we'll get intense blue color, then we'll get light blue color, green color and green shade color. The green shade indicate that we are at the verge of end point. So based on the intensity of color, we have to add the potassium dichromate solution into the reaction mixture. So now we can add around 2 to 3 ml of the potassium dichromate solution. As well, remove the drop of the reaction mixture and bring it in contact with indicator. So now it is green color. Now we can add around 0.5 to 1 ml of potassium dichromate solution and bring it in contact with the indicator. Is also green color. Add 0.5 to 1 ml of potassium dichromate. Mix well. Bring it in contact with the indicator. Drop. So this is green shade. The green shade indicates that we are at the verge of end point. I'll show you one more time. So this is green shade. Now add 2 to 3 drops of potassium dichromate solution. Remove the drop of the reaction mixture and bring it in contact with the indicator. So there is no green color or blue color. Now touch the drop of the indicator. We'll get intense deep brown color. So this indicates that you have oxidized all ferrous ions to ferric ions. When these ferric ions are in contact with potassium ferricyanide, we'll get this color. This is due to the formation of complex between ferric and ferricyanide, that is known as ferric ferricyanide. After getting this color, take out the burette from the stand and read the values.